Training deep learning models. For anyone deeply involved in AI, you know it's a monumental undertaking. We're talking about massive investments of time, significant computational resources, and often a lot of meticulous fine-tuning to get a model just right. But what if there was a remarkably simple yet profoundly powerful technique that could dramatically, accelerate that entire process and maybe even enhance the model's performance? Today, we're taking a deep dive into precisely such a technique: weight averaging. Now, the core idea, it's actually been around for decades, but its resurgence and impressive impact in modern deep learning, well, especially with the enormous models dominating the landscape today, it's truly making waves. Our focus for this deep dive is a really comprehensive evaluation, arguably the largest and most rigorous of its kind. It's titled When, Where, and Why to Average Weights. This groundbreaking work comes from researchers Niccolò Ajroldi, Antonio Orvieto, and Jonas Geiping. And they didn't just casually test this concept, no, they put it through an exhaustive, large-scale benchmark known as AlgoPerf to thoroughly scrutinize its effectiveness. So, our mission today is to extract the most crucial nuggets of knowledge from their meticulous research. You'll discover how weight averaging can radically speed up training, subtly but consistently improve model performance, and how it relates to a very common practice in deep learning rate decay. Get ready for some genuine aha moments that could fundamentally shift how you approach optimizing your own models, or even just how you understand the cutting edge of AI training. Okay, let's unpack this. We hear weight averaging. What exactly does that mean in the context of deep learning?
Right. So at its core, weight averaging, or WA, it's a technique where you essentially combine multiple sets of a model's weights. Those numerical parameters that define what the model has learned. You combine them into a single, usually more robust final model.
Okay, combining weights. How do you do that practically?
Well, there are a couple of main ways. You can do it online, so you're continuously averaging the weights as your training actually progresses. Or you can do it post hoc, where you save various snapshots, checkpoints of your model during training, and then average them together later.
Interesting. So online or after the fact?
Exactly. And what's really compelling here is that this isn't some brand new idea. Its theoretical roots go way back. We're talking foundational work in optimization by Polyak in 1990 and Ruppert in 1988.
Wow, back that far.
Yeah, which is why you often hear it called Polyak-Ruppert averaging. It's deeply rooted in the mathematics of convex optimization. It essentially helps to, let's say, smooth out the noise you inherently get with gradient descent, leading to more stable, predictable convergence.
Okay, so we know what it is and its impressive historical roots. But the real magic, and what makes practitioners like us pay attention, is why. Why bother doing this? What are the big advantages for today's complex models?
Right, the why. And the benefits are, frankly, quite significant. They touch on almost every aspect of training. First off, it consistently leads to improved generalization.
Meaning it works better on new data it hasn't seen.
Precisely, which is the ultimate goal, right? And the mechanism behind this is fascinating. Averaging helps the model find these wider minima in the loss landscape.
Wider minima, like flatter valleys in the error surface?
Exactly. Think of it like smoothing out a really rugged, bumpy terrain. Instead of getting stuck in a narrow, sharp crevice that might be great for the training data, but fragile for new stuff, averaging helps you settle into a broad, stable valley.
Okay, so more stable, less sensitive to small changes.
Right. That stability makes it more robust. Secondly, and this is huge for practical applications, it demonstrably reduces training time. The study we're diving into provides really strong evidence that it significantly accelerates the whole training process.
Faster training is always good. What else?
Well, building on that stability point, it increases robustness. Models become inherently more stable against variations in data or even training conditions. It also helps in smoothing those lost landscapes, which makes the optimization itself more stable. And it accelerates convergence, helps models reach good solutions faster.
So better generalization, faster training, more robust. Sounds great. Is it complex to implement?
That's the beauty of it. Critically, it achieves all these gains with minimal extra implementation and memory cost. It's almost like a free lunch for practitioners, which is pretty appealing.
Okay, free lunch is hard to pass up. How did this concept, evolve specifically within deep learning, from theory to practice?
Well, while the origins are old, it's been used, sometimes quietly, for a while in DL. You can see its influence in some really foundational work, like Segedi et al.'s Inception architecture back in 2016, the huge Vaswani et al. Paper on transformers in 2017, and Merdi et al.'s work on LSTMs, also around 2017. They all sort of used averaging principles to boost performance.
So it was hiding in plain sight, almost?
In a way, yeah. But more recently, there was this paper by Ismatanov et al. In 2019 introducing stochastic weight averaging, or SWA. That really sparked renewed interest, both academic and practical. SWA clearly showed how averaging points along the SGD path leads to those wider minima and better generalization.
Okay, so SBA kicked things off again, and this paper we're looking at focuses on specific types.
Exactly. This paper, When, Where, and Why, it really digs into evaluating two key modern flavors. First, there's latest weight averaging, or LAWE. This came from Cador in 2022. It's an online method, averaging only the most recent checkpoints within a rolling window. Think of it like a circular queue of a fixed length L.
Like averaging the last 10 steps, for example?
Something like that, yeah. It's particularly noted for its speed-up benefits, especially in pre-training those huge language models. The second main one is exponential moving averaging, or EMA. This maintains an exponential moving average, giving more weight to the most recent parameters using a discount factor, usually called gamma or beta.
EMA. I've definitely seen that mentioned with JANs and diffusion models.
Absolutely. It's become pretty much indispensable in areas like high-quality image synthesis. It's key to how models like Stable Diffusion work so well.
That's a great distinction. So LAWA and EMA are the two main flavors they looked at. How do they practically differ? You mentioned EMA is big in diffusion models. Why is that?
Yeah, the fundamental difference is really in their memory and how they weigh past information. LAWA is like looking at a fixed-size photo album of your most recent model states. Every photo in that album, every checkpoint in that window gets equal weight in the average.
Okay, equal weighting within the window.
Right. It's a clean, discrete average of a specific set of recent steps. EMA, though, is more like a fading memory. The very latest model states have the most influence, the most weight, but older ones gradually fade out. Their influence decreases exponentially over time.
So it forgets older stuff faster.
Exactly.
Yeah.
And this exponential decay means you don't actually need to store that entire window of past checkpoints explicitly. You just update a running average with each new set of weights.
Which saves memory.
Hugely. It makes EMA incredibly memory efficient. You don't need to store all those past snapshots, which is a massive practical advantage when you're dealing with memory constraints. And that's precisely why it's so popular for those gigantic image synthesis models. Memory is often the bottleneck there.
Gotcha. LWA is equal weight in a window. EMA is exponential decay, much lighter on memory. Okay, so we get the what and why, the different types. But for us, the learners and practitioners, how did these researchers actually put weight averaging to the test? What was their experimental setup like? How rigorous was it?
Right, the how. They used AlgoPerf. It's a large-scale, unified benchmark introduced by Dahl and others in 2023. And AlgoPerf isn't just any benchmark. It's specifically designed for optimizing algorithms. This lets you draw really robust conclusions because you're testing against strong, heavily tuned baselines.
Meaning you're not just beating a straw man, you're comparing against already good methods.
Exactly. You're comparing against the state of the art, or close to it. The researchers used two main evaluation strategies. Strategy A was all about efficiency. They'd fix a challenging target loss value and then measure the runtime either in training steps or actual GPU hours needed to hit that target.
How fast can you get there?
Precisely.
Yeah.
Strategy B focused on generalization. Here, they'd fix a computational budget, like say 100 GPU hours, and then compare the performance of different models within that fixed budget.
Who gets the best result for the same cost?
Right. And to make sure the findings weren't just specific to one type of problem, their evaluation spanned a really diverse set of workloads. 7 different architectures and data sets. We're talking recommendation systems with DLRM-SMAL on Credia 1TB, medical imaging with UNet on FastMRI, image classification with VIT on ImageNet, GraphML with a GNN on OGBG, machine translation with Transformer Big on WMT, and even speech recognition with Conformer and deep speech on LibreSpeech.
Wow, that's a broad sweep, covering a lot of ground.
Definitely. For their baseline optimizers, they mainly used NeedOMW, which is a pretty common and effective choice. But they also tested against the more sophisticated distributed shampoo, which is a powerful second-order method.
Okay, solid baselines. What about randomness? Training can be variable.
Good point. To control for that variability and ensure the results were reliable, they ran all experiments rigorously, using 3 different random seeds. That's standard practice for scientific robustness.
Okay, sounds like a very thorough setup. All right, let's get to the results. The first big takeaway, speed. Can weight averaging actually make deep learning models train significantly faster? Because, That's the dream for many of us.
Unequivocally, yes. The study provides really strong quantitative proof. It dramatically accelerates training. They estimate a pretty remarkable 12% reduction in GPU hours needed to train the entire AlgoPerf suite when using LUA on top of NetMW.
12% across that whole diverse set. That's huge.
It really is. Let's put that into perspective. For large-scale training, where models can run for days or weeks, costing thousands, maybe millions, a 12% reduction isn't just significant. It translates directly into substantial cost savings, a lower carbon footprint, and faster iteration cycles for development teams. It's a massive efficiency gain.
And that speed up also means you could stop earlier.
Exactly. It implies that if you have a target validation score you're aiming for, weight averaging can be used effectively for early stopping. Okay. You reach your desired performance threshold sooner, saving potentially significant compute costs. It's like having an invisible accelerator pedal. A 12% reduction. That's seriously impactful. But okay, what about the details? The averaging horizon. How long do you actually average for? Is there a magic number, or is more always better? That sounds tricky to tune.
That's a critical practical question for sure. The averaging horizon refers to, well, the span of the window for LAWA, or the effective memory for UME, and also how often you update the average. The study found that moderate averaging is key. There seems to be a generalizable sweet spot around 1% of the total training budget for the averaging window size.
1%. That seems quite small. It does sound small, but it consistently yielded optimal results across various tasks in their tests. The research also clearly showed that excessively small or excessively large horizons are less effective. Too small, and you don't get enough smoothing benefit. Too large, and you might be averaging in outdated or less relevant information from much earlier in training.
So a balance. How hard is it to find that sweet spot?
Well, what's also interesting here is that LSI in particular showed pretty good robustness to the hyperparameter choices. This means a relatively decent range of settings for its averaging horizon still delivered strong performance. So it seems quite forgiving in practice, which is nice.
That's definitely a plus. Less fiddly tuning.
Right. And another intriguing point, WA maintains its efficiency gains even if you apply it to a suboptimal baseline optimizer, or maybe with varied learning rates. It reliably reaches the target faster anyway. It suggests provides benefits even if your initial optimizer setup isn't perfectly tuned, almost like a safety net.
That's a huge relief for anyone who's wrestled with hyperparameter tuning. Okay, but let's play devil's advocate. What if I'm already using something super advanced, like that distributed shampoo you mentioned, which is already highly optimized? Are we still talking meaningful gains with weight averaging then, or just tiny improvements that might not be worth adding another step?
That's a totally fair challenge, and it's exactly why they included distributed shampoo, which remember was the top algorithm in the AlgoPerf competition. It's a beast. And the answer is, yes, it still helps. Even with such an advanced, highly efficient optimizer, WA consistently enhanced performance. It allowed models to reach targets sooner, and interestingly, even reduced the variability or randomness of the baseline optimizer's results.
Even reduced variability. Okay, that's compelling.
Yeah, it strongly emphasizes that the benefits of weight averaging aren't just about compensating for slower optimizers. It offers inherent advantages, regardless of the underlying optimization method. It's like putting a supercharger on an already high-performance engine. Still makes it better.
Okay, point taken. Speed is a massive win. But beyond just speed, does weight averaging actually make the models better? Better at generalizing to new data, making them more useful in the real world?
Yes, it does. But here, the gains are perhaps a bit more moderate compared to those dramatic efficiency improvements we just discussed. WA does consistently improve generalization performance over the baseline. It achieves slightly better validation scores. They saw noticeable improvements, for instance, in workloads like machine translation with WMT.
Slightly better.
Yeah.
Okay. Is it always better, or does it depend?
Well, a key observation they made, which they've called the shrinking gap, is really crucial for practitioners. While the generalization benefits are more pronounced in the early stages of training, as training goes on and the model converges, especially when you apply learning rate decay, that generalization gap between the average models and the baselines tends to shrink.
Ah, so the advantage lessens over time.
It seems so. What this tells us is that weight averaging gives you a fantastic early boost in generalization, getting you to a good solution on new data quickly. But its role might shift later in training. It puts you on the fast track to a great initial solution. But as you continue to fine-tune, maybe with aggressive learning rate decay, other techniques might become equally or maybe even more impactful for squeezing out those last fractions of a percent in performance.
Interesting. So great for getting there fast, but maybe not the final optimization step.
Potentially, yeah. And in terms of stability, with suboptimal baselines for generalization, average checkpoints do closely track the baseline's performance. However, if the baseline is just failing spectacularly, say the learning rate is way off, WA usually can't completely rescue it. It seems to help good baselines become marginally better, rather than fixing fundamentally broken ones.
That makes sense. Okay, this leads to a really important question, one I know I grapple with, and many others too. We rely heavily on learning rate decay schedules to fine-tune our models, push them to their best performance. It's standard practice. Can weight averaging just replace that? Can I just average weights and skip the whole complex learning rate schedule thing?
That's the million-dollar question, isn't it? It's a complex relationship, quite nuanced. The short answer is generally no. It usually cannot completely replace learning rate decay.
Okay, not a total replacement. Why not? They seem related.
There's definitely an intuitive link. Averaging weights does effectively reduce noise in the optimization process, which acts somewhat like lowering the learning rate. And indeed, the average models often closely track the performance of runs that use faster decay schedules. However, the study's general conclusion is that WA, by itself, particularly when the average weights aren't directly fed back into the optimization updates, typically yields inferior final performance compared to fully annealing the learning rate down towards zero.
Inferior. So LRDecay still wins for peak performance, usually?
Usually, yes. But what's fascinating here are the nuances and exceptions. For some specific workloads, like the CRUDIA1TB recommendation task and the OGBG graph task, WA could actually achieve the target performance without needing to significantly lower the learning rate.
Oh, so sometimes it can work alone.
In specific cases, it seems so. But crucially, the research found that combining WA with traditional learning rate annealing often yields optimal performance. It slightly improves both generalization and efficiency simultaneously.
So they're better together, like peanut butter and jelly.
Exactly. It strongly suggests there are complementary techniques, each offering distinct advantages, rather than being substitutable. They work best as a team.
That's really useful. Use both.
And one final point on this. The benefits of WA tend to diminish as the learning rate is fully annealed, like right down to zero. This implies its biggest impact is felt when the learning rate is still relatively high and the optimization process is still more dynamic and, well, noisy.
Okay, so it helps most when things are still turbulent early on. That's a vital distinction for planning training. Okay, that clarifies the LR-decay relationship. Now, beyond the controlled environment of AlgoPerf, how does weight averaging perform in the wild? Like, say, training a large language model. That's super relevant right now and notoriously compute intensive.
Yeah, that was a crucial additional analysis they did, moving beyond the benchmark to a really practical large-scale application. They ran an experiment on a 124 million parameter decoder-only transformer, think something architecturally similar to GPT-2. They trained it on the fine WebEDU dataset, aiming for a specific target validation loss.
Okay, a real-world LLM setup.
Yeah.
And the results.
The results here were particularly striking. Both Laowa and Ima achieved substantial speedups. We're talking roughly 30% faster to reach the target validation loss compared to the standard AtomW baseline.
30% faster for an LLM. That's huge.
Absolutely huge. It unequivocally highlights its significant practical value and efficiency for training these large models, where honestly, every percentage point of speedup translates into massive savings in time and compute cost.
Wow. And between Laowa and Ima in this case.
Well, what's particularly compelling about this finding is that when it was properly tuned, Ima managed to match Laowa's performance on this specific task.
Ima matched Laowa, but you said Ima uses less memory.
Exactly. While requiring only a fraction of the memory. For anyone training models with billions of parameters where memory often becomes the real bottleneck, not just compute, this is a massive practical win. Getting the same speed up with way less memory, that's fantastic.
Okay, that is a big deal for LLMs, but you said properly tuned Ima. Is it tricky?
It does require some attention, yeah. It highlights the sensitivity of Ima's hyperparameters. Specifically, its update frequency, often called nu, which controls how often you update the average, and its discount factor, beta, which controls how quickly old information fades. Proper tuning is essential. They found, for instance, that small values of nu paired well with large values of beta, and vice versa. So there's an interplay. It's not quite fire and forget like Laowa might sometimes feel, but the payoff for tuning Ima seems considerable, especially given the memory savings.
Right, a bit more tuning for potentially big memory gains. Got it. Okay, so every deep dive, every research paper has its limits. What did the researchers themselves identify as the boundaries of their analysis here, and what's next for weight averaging research?
Good question. The primary limitation they acknowledged is that their analysis focused mainly on Nadam, LW, and Adam W as the baseline optimizers. Although, as we discussed, they did include distributed shampoo, which adds some breadth.
So mostly Atom family optimizers?
Right. This naturally raises the question, what happens when you combine WA with other, perhaps even more different, optimization algorithms? Future work could definitely explore WA with a broader range of optimizers. Especially interesting would be looking at newer schedule-free methods.
Schedule-free, you mean optimizers that don't need a learning rate schedule?
Exactly. Methods that aim to replace traditional LR schedules entirely by adapting inherently. Imagine combining an optimizer like that with weight averaging. It could be a really powerful combination. That's a clear direction for future research.
Interesting. Okay, so let's zoom out. Bringing it all together, what does this mean for us? For the learners, the engineers, the researchers listening, what's the big picture takeaway from this deep dive into when, where, and why to average weights?
I think the overarching conclusion is crystal clear. Weight averaging is fundamentally a simple yet powerful technique. It's not overly complicated conceptually or to implement, and it offers substantial efficiency gains. Just remember that 12% GPU hour reduction across AlgoPerf and that impressive 30% speed up for the language model example. Plus, it consistently provides marginally better validation scores, so a small boost in quality too.
Simple, faster, slightly better. Seems like a win-win-win.
Pretty much. For practical applications, especially large-scale model development, it's a highly practical tool. A key reason is that it allows you to access a better performing model during training without having to prematurely decay the learning rate. This effectively pushes models closer to what they call the Pareto optimality of loss versus training time.
Meaning you get great performance for significantly less compute effort.
Exactly. You get more bang for your buck, compute-wise. It's a method that, even though it doesn't usually directly influence the optimization updates themselves, can dramatically reduce training time and often improve model quality. The study really makes a strong case for broader adoption of these methods across the deep learning community.
Wow, that was a truly insightful deep dive into weight averaging. It's really clear this isn't just some, academic curiosity. It's a robust, practical technique with real, tangible impact on the efficiency and performance of deep learning models, especially at scale. What stands out most to you from this deep dive? For me.
Honestly, it's the idea that such a seemingly simple averaging trick can save 12% of GPU hours across such diverse models, or make training 30% faster for something as complex as an LLM, all while subtly improving generalization and stability. It's genuinely profound. It really does feel like finding a hidden turbo button for your training process that was maybe there all along. Okay, here's a final provocative thought for you, for everyone listening. If merely averaging model weights can yield such significant, almost free, improvements in training efficiency and performance, what other deceptively simple techniques might be hiding in plain sight, just waiting to push the boundaries of large-scale AI training even further? What free lunch are we missing next in this incredibly complex field? Something to ponder.
We really hope this deep dive encourages you to look a little closer at the underlying mechanisms of the models you work with or interact with every day. And maybe, just maybe, it inspires your next big aha moment. Until next time, keep diving deep.